Alright, we're going to move on to 4.2. But all I'm going to focus about 4.2 is just being able to graph and do transformations or translations to the exponential function. How do you spell exponential function? That's a good question. Exponential function. So up until now we hadn't seen any new functions. All we saw was absolute value, square roots, cubes, linear functions, quadratic functions. But now here's a new function that we're going to look at, and that's this exponential function. What the exponential function looks like, again, we're going to use function notation. And we're going to see the graph right now that it does pass the vertical line test, and it also happens to pass the vertical line test and the horizontal line test, meaning that vertical line test always has to pass first. That makes it a function. And then if it happens to pass the horizontal line test, that makes it a one-to-one function, meaning that it will have an inverse, and we're going to talk about the inverse after. But this is what the exponential function looks like. So we're going to have a to the x, where a can be any number. Normally we deal with a being greater than 0. But there's different situations that happen depending if a is in between 0 and 1 or if a is bigger than 1. But we can talk about that after. But for starters, let's just look at an example, because I just want to focus on how the graph of this exponential function looks like. So example, let's graph f of x equal to 2 to the x. So I'm going to make a big graph over here, because I'm going to make a table. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So, remember I said the first time we ever learned how to graph anything, it was going to be the most important way we learned how to graph. Because even though we graph linear equations and we use slope-intercept form, that was strictly only for linear functions. If you wanted to graph anything else, the best way to do that was going to be using a table. But in this case, since we're not using y, it's not the xy table, it's the f of x table. And then we're going to choose some values. So let's try -2, -1, 0, 1, 2, and maybe 3, just so we can see what's happening on both sides of this graph. Now, all that's going to happen is you're going to take that x, which is -2, you replace it for your x and f of x, which is going to replace the x in your 2 to the x. Remember, that's a power. So that's going to be 2 to the -2 power. Which, if you remember what negatives do, I'm going to do it over here on the side, but if you remember this rule of exponent, that if you have a negative exponent, that always rewrites your expression into a fraction. So if we have 2 to the -2 power, that's going to become 1 over 2 squared without that negative, which then will leave us with 1 over, and 2 squared gives us 4. So this becomes 1/4. Now, similarly, again, I'm not going to write f of -1 for all these numbers. So it's going to be 2 to the -1 power. We use the same rule of exponent again, gives us 1/2. And then 2 to the 0 power, another rule of exponent. Anything to the power of 0 is always equal to 1. So this simplifies to 1. And then 2 to the power of 1 is just 2. 2 squared is just 4. And 2 cubed is just 8. And you can try to use a half, but doing 2 to the half power might look a little funny. So I'd rather not use those numbers, but they're perfectly okay to use. So now when we graph, so we have 1 point here at -2. So at this -2, we have a point at 1/4. So 1/4, if this is 1, that means 1/4 is just a quarter of the way up. So we have a point right about here. And then when we get to -1, it goes a little higher. It's now at a half, so it's halfway between a 0 and 1. And when our 0 is x, we actually have a point at 1. At 1, we jump to 2. But from 2, we go to 4. So it jumps now. It goes from 2, 3, all the way to 4. And then at 3, it jumps again all the way to 8. So this stopped at 4, 5, 6. Let me see if I extend it. 7, 8. And you can see what's happening to the graph. If I follow, then you have to ask yourself, is this ever able to equal 0? Can you think of any number that you put on the x that's going to give us 0? We tried negatives, that still gave us a number. We tried 0 and that gave us 1. And we tried positive numbers and that only made it much, much, much bigger. Meaning that no, that's impossible. That you can never find any value of x that will make this 0. So what ends up happening is that it just keeps getting closer and closer and closer, but it never actually touches the x-axis. Eventually we're going to talk about something called asymptotes. Asymptotes are are lines that your graph just cannot cross and will never cross. So we can see that here, that this horizontal line is sort of like a horizontal asymptote, meaning it's going to get closer and closer and closer and closer and closer, but it will never actually cross the x-axis. So this is what happens for an exponential function. It starts really low and then it abruptly starts growing really, 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 really fast. You've noticed if we put in 4, that would be somewhere all the way up there. So it starts shooting up really, really quick. Maybe you've heard that expression when people say that something has grown exponentially. That means that something is growing extremely fast. It means that maybe it was kind of growing slowly and then before you knew it just shot straight up. It almost looks like a vertical line going up. So if you ever hear anyone use that expression, that means that something is growing really, really fast, really quickly. Because from -2 to -1, it just went up a quarter. But from -1 to 0, it went up a half. But then from 0 to 1, it went up 1. But then from 1 to 2, it went up 2. From 2 to 3, it went up 4. So it started growing much quicker. And you can only imagine what's happening at 10 or 1,000. Shoots up really, really high. So that's what these will look like. And that is true for whenever A, so this A, so all of these will look for whenever A is greater than 1. What I mean by that is, let's say if you tried graphing, so this is, we'll say this is f of x. Let's say you tried graphing another function. And then this is just me giving you rough sketches. If you want, you can go ahead and try to graph them by hand. Or you can use your Desmos online just so you can see what's happening. But remember, when it came to transformations, it was important that we knew the parent function. So we had to know what the original function looks like. So let's say now I had asked you to graph, let's say, I'll put it down here. G of x is equal to 3x. So what ends up happening here is still the same. It starts really low on one side. But then at 1, you notice that if you plug in 1 into that x, it's going to be 3. So I mean that this one, instead of being at 2, it's going to be at 3. If you put a 2, that's actually going to be 2 3 squared, which is 9. So that's going to jump up here. So what ends up happening, it just grows much quicker, but then still continues on like that. And let's say if you wanted something even bigger, let's say if you do h of x to the 4 to the x. So that means at this one, it's actually here now. So that means it's going to look much, much higher. So that this is what 3 to the x looks like. This is what 4 to the x would roughly look like. And this is what 2 to the x looks like. And you wouldn't use 1 to the x because that would just make it a straight line. It would make it a horizontal line. X wouldn't really change anything. So, because when you have 1 to any power, it will always give you 1, meaning it will just leave you with a horizontal line. So, as this a keeps getting bigger, your exponential function just grows faster and faster and faster. But hopefully you noticed when I was sketching these, something happened. And that's right here. That point is 0, 1. That's important because it sort of gives us a point to work off of when we're doing these transformations to these graphs. Let's say we want to shift them left, right, up, down. Because remember, when we did transformations, the first thing you had to know was the parent function. That was the first thing we did. And the second thing, remember, we start from inside out. So the first thing was to see if anything was multiplying 2x on the inside, or if any negative was multiplying inside. And then if anything was adding or subtracting inside. And then we worked our way out if anything was multiplying outside. And lastly, we checked if anything was adding or subtracting outside. So, and remember, when you're working inside, so that's the inside part. This is the out part. The first one is just looking for the parent function. And remember, inside behaves opposite of what you think it should do. So, a number bigger than 1 actually does a horizontal shrink. Bigger than 1. If it's in between 0 and 1, it actually does a horizontal stretch. Where the negative, in the inside, does a reflection. What it does, it just changes all the x coordinates into negatives. So it switches whatever's on the right to the left or left to right. And then inside, adding actually moves it to the left, but subtraction moves it to the right. So don't forget that. Adding left, subtraction right. And then outside, everything behaves the way it's supposed to. So if you multiply by a number bigger than 1 outside, that does a vertical stretch. If you multiply between a number between 0 and 1, it does a vertical shrink. Well, again, opposite. Inside would have been number bigger than 1. It's a horizontal shrink. Maybe I said that backwards, but a number bigger than 1 is a horizontal shrink. A number in between 0 and 1 is a horizontal stretch. Because it does opposite of what you think it should do. And don't forget, the negative outside does a reflection on the x. So that changes all the y coordinates below and all the ones that are below above, if there are any. In this case, there aren't any, so we wouldn't actually flip it. And then the positive and negative outside shifts it up and down. So we'll look at some examples of this. Just because I want to do a rough sketch, but we have to be able to recognize what the graph looks like. But we see 2, 3, 4, and you can sort of see the pattern, what's happening. 2, 3, 4, 5 would just be even bigger. 6, 7, 8, 9, and just keep getting bigger and bigger and bigger and bigger. But let's do some examples of translations. All right, let's look at a couple examples of graphing these exponential functions, but we're going to use transformation to do that. So, for example, we have, let's graph f of x equals 3x minus 2 plus 4. So remember I said when we want to establish is being able to find the the parent function. That's our first thing. Parent function. Which I know my parent function here is 3 to the x. Which we already know how 3 to the x looks. So I can start by graphing the parent function. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So, and we also know this 1 point here for reference, because we know the original one, at least, is 3 to the x, has an original point that goes here, and we know it starts low and then goes up. Again, we just have to know a rough sketch. If you want to use exact points, again, you always can, but I'm just going off this 1 point here to help us sort of reference. But remember, at the same time, there is this line here. Hopefully you guys can see. I'm drawing a line here. That's not the actual exponential. There's this horizontal line here that it cannot cross. Because remember, this 3 to the x cannot be equal to 0. It's just impossible. And it can never be negative. That's why the graph exists above the x-axis and never crosses it. Alright, the next thing we have to look at is if there's anything multiplying to the x inside the function. It's either a number or if it's a negative. And by inside, in this case now, when we're looking at absolute values, it was literally inside the absolute value. For quadratics, it was inside the absolute value. For square roots, it was literally inside the radical. Here, when I say inside, it's happening in the exponent. And I could see right here, there's nothing actually multiplying to the x. Not a constant or a negative. So that one, check. There's nothing we need to do. But now we want to see if there's anything adding or subtracting inside. And we see that there is. There's a negative. But remember, subtracting inside, that actually means you're going to move it to the right. So just so we have a point for reference, what's happening here, so this coordinate here is 0, 1. What we're changing is we're instead of subtract, remember, we do opposite of what you think it should do. So if you're subtracting by 2, you're actually adding by 2 to this x coordinate. So that point actually gets moved to 2, 1. And then here's the graph. Whoops. The graph is here now. So everything gets shifted. Again, it's still not going across. It's still not going across the x-axis. It's still that horizontal asymptote. Now we need to see if anything is multiplying outside, either by a constant or if there's a negative multiplying outside. If there's a negative and we can see right here in front of this 3, there's nothing multiplying. So that one's done. And now we just have to see if anything is adding or subtracting outside. But remember, adding or subtracting outside behaves the way it's supposed to. So now that means it was supposed to be plus c. And what's happening is that we're actually adding by a 4. So that means it's going to go up because it behaves the way it's supposed to. So what's changing this time is the x coordinate. The y coordinate is the one that's changing. So we're going to actually add 4 to this coordinate. So it actually moves up 1, 2, 3, 4. But remember I said there's this horizontal line here that these graphs are not crossing whatsoever. So you actually have to take that horizontal line with you. That's one of the trickiest parts. So it goes up 1, 2, 3, 4. There's this horizontal line here that this graph is not going to cross. It used to be here at the x-axis and it went up 1, 2, 3, 4 because we moved it up 4 units. But this point is still in the same place. We're not going to cross that line. We know we intersect this point and then it has to go up. And that's the final graph. This is your f of x here. We've shifted it. We're able to graph it. So, again, the big thing is knowing the parent function and knowing this horizontal asymptote that's here. And make sure if you shift up or down, Remember, left or right doesn't change anything. We move this graph left and right, but that horizontal line moving left or right doesn't do anything. But going up or down will have to change, so you want to be careful with that. Let's look at another example. With this example, we're going to do a slight trick to help us graph it. Just because sometimes it could be confusing when you're doing it. So, let me show you. So we have, let's say, let me make sure you guys can see. Let's just say g of x now is equal to, let's try 1/3, or yeah, 1/3 to the x plus 2. All right, at first glance, you should see there's an issue here, and that's this number. Because the only way, if I'm trying to find a parent function, the only functions we've looked at was when this number was bigger than 1. So there's a trick that we can do, and that trick has to do, I'm going to put it over here on this box. It's using the rule of exponents with negative exponents. And you can always rewrite a negative exponent as a fraction. I did that in the previous examples. So what I'm going to do here is, instead of writing 1/3, I'm going to just use this rule backwards. I can rewrite this as 3 to the negative 1 power. So this is equivalent of saying 3 to the negative 1 power to the x plus 2. And then there's a second rule, that a rule of exponents, maybe you remember. When you raise a power to a power, you can actually multiply those powers together. Here we're actually using this rule in this direction. This one we used it in the opposite direction. Because what's going to happen here is you're going to multiply that negative 1 with that x to leave you with 3 to the negative x plus 2. Now I can graph this because I know the parent function. So this was the one that, and this is for when this number here is in between 0 and 1. That happens every single time. So if we're looking at the function, the parent function 3 to the x again, so we know what that looks like. Don't forget, there's actually an asymptote here that I forgot to write again. So again, I'm just listing points. So then right here, I have my dot, and I know this is what 3 to the x looks like. Something like that. Again, it's just a rough sketch. But now, I need to see if anything is multiplying inside. If it's either a number or a negative. And I can see here, I switched it to have a negative in there. So when you have a negative inside, what's happening is you're taking all the x coordinates, all the positive x, and you're multiplying them by a negative number. You're taking all these x coordinates and multiplying them by a negative number. So that ends up doing all your positive numbers get switched to negative, and then all your negative numbers get switched to positives. And what it is just a reflection on the y-axis. So whatever's on the right hand side goes to the left, whatever's on the left goes to the right. So now we did that, so check. We knew the parent function, we have this. Now, and this is going to happen every single time. This could have been a half, a fourth, a 1/5. This whole trick happens every single time. Again, you could have been dealing with, let me use a different color. We could have been using 1/2 to the x. Again, that's the same thing as 2 to the negative x, using this same sort of argument here. You can always do that. It could be a third, a fourth, a fifth, a sixth, a seventh, and it's always going to mean that there's this reflection on the y-axis happening. Now we see if there's anything adding or subtracting inside, which we can see there's nothing adding to that x. So we're done there. Now we want to see if anything is multiplying outside, either a number or a negative, and there's nothing outside. Lastly, is there anything adding or subtracting outside? And there is. There's a 2. But remember, outside behaves the way it's supposed to. So that 2 actually moves it up. But don't forget, you also need to move that horizontal asymptote. Because if you see, look, this just gets closer and closer to the x-axis. You're going to have to move it up 2. So that's not 12. You're going to move it up 2. So here, it's going to be this. And then this point moves up 2 as well. 1, 2. And then that's where your phone. Okay, sorry, the video got cut off right at the end. But I was just finishing up here that here would be our g of x, because our horizontal asymptote moved up 2, and then the point that we know also moves up 2. Just a good point of reference to help us draw this exponential. Again, you can always graph these by making a table, but to sort of apply the transformations that we learned before, I just wanted a rough sketch of what the graph would look like. Now, there's an important exponential that is going to show up in many different places if you continue in mathematics. So, I want to graph that one next, just so we can see what it looks like. So, we'll do this, will be the last example. So it'd be h of x equal to, oops, I already messed up. H of x equal to negative e to the x minus 1. And then we'll put minus 3 here. So there's a lot going on here. The tricky part about this is the fact that there's this letter now. Now we're dealing with this letter E. But remember, when the original one I showed you, that had to do with, so this can always be bigger, it's always bigger than 0. But all the ones that look like this are the ones that are strictly greater than 1. But we did just see an example of where it was actually in between 0 and 1, the 1/3. What that means is just all these graphs in the other direction like this. That would be 1/4 x, this would be 1/3 x, this would be 1/2 x. It just sort of does a reflection on the y-axis. Now, we need to ask ourselves, what does this number mean? Is it going to be the ones that's reflected on the y-axis, or is it going to be like these original parent functions? And if you look on your calculator, so I keep getting notifications for the curfew. So every time I get a notification, it pauses my video, and then sometimes I don't realize it, and I have to start the video again. So sorry about that. But like I was saying, if you looked at your calculator, E is equal to 2.71. So that means that this is definitely greater than 1. So it's going to look like one of these two. In particular, it's going to be somewhere in between this 2 to the x and 3 to the x. So because you notice, look, it keeps going higher as that number increases. So just by observation, it's going to be in between. So we can graph that. So we'll say the parent function in this situation is e to the x. Because remember, you're just sort of taking off all these extra little pieces. But I already know roughly what it's going to look like. Just because we know that it's bigger. Hold on. I was supposed to do this. I keep forgetting. Because there's supposed to be this horizontal line here. And I'm just going to do a rough sketch. Just because we've seen a couple examples already. So I'm just going to rough sketch it. So it's going, because it's in between 2 and 3. it's going to look something like this. And it always intersects this point. Because if you put a 0 inside this x, it's always going to give you 1. So this point is always here for these. Now we need to see if anything is multiplying inside the function. Or I guess in this case, h of x. Either a negative or a constant, and there's nothing multiplying. Now I need to see if anything is adding or subtracting inside. Which there is. There's a subtraction. So the negative means you're going to the right. If it was positive, that means that you're going to go to the left. So I'm going to go to the right 1 unit. So now this is going to get shifted. Again, it's just very slightly, but it's getting shifted over to the right by 1 point. And then you want to see if there's anything multiplying outside the function, either a constant or a negative. And there is this negative outside of the function. And what that means now is that everything, there's a reflection on the x-axis. So whatever points are above here, so again, this point became -1, 1. What's happening is that we're going to multiply a negative to that x-coordinate, bringing it down below the x-axis. So everything that was above is just getting reflected below, and will look like this. Just getting reflected downward. And then lastly, we need to see if anything is adding or subtracting outside. Which there's a subtracting 3, so that means you're going to go down. But what's also going down is this horizontal asymptote. It's going down 1, 2, 3, 4. So it's going to be here. And then that point, same thing, is coming down 1, 2, 3, 4. And this is where the graph is going to end. That's going to be my h of x here. And I know that because it's bigger than 1. So it's going to start this initial parent graph. There's nothing multiplying. That -1 shifts it to the right, because now it's opposite of what you think it should do. That negative outside reflects it down. And then that -3 brings it down 3. So, oops, I made a mistake. It's only supposed to bring it down 3. We brought it down 1, 2, 3, 4. My bad. So, scratch that. So sorry. That was my fault. I think I was thinking about the previous example, and that's why I did 4, but it's supposed to be 3. So you go down 1, 2, 3. This is where it's going to finish. And that point is coming down 1, 2, 3 as well. And this will be the parent function right there. That's our true h of x, not this one. I just shifted it down too much. Hopefully that doesn't cause too much confusion. But try graphing some of these. Again, all I care is about a rough sketch. It doesn't have to be perfect. As long as you're understanding what's happening and what the graph looks like. Let me give you a couple examples for homework. Again, not too much. We're just doing small rough sketches of these. I'm not expecting too much. So let's graph. So we'll do 15. Try 16. 17. 19. And then, so for these next ones, you're going to be using transformations to graph them. So we have 23. Let's do 25, 27, 28, and 31. Oh, I should have put 29 in there and then 31. So again, just give me a rough sketch of these problems and see what you end up with. Oh, let me give couple more. Sorry. Let's try 40 and 43. Again, these aren't too bad. So it's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right. Try those. Again, I'll be posting a little more, but this is what's going to be the transformations and the composition, the inverses, and this is what's going to be on the test. It sort of all goes hand in hand together. So all I have to do is teach about logarithms, how to graph them, how to do transformations, and that will be it. It's going to be a whole test of transformations and doing composition and checking inverses. So try to watch this video. Thank you.